we had discussed the no slip boundary condition and the hard wall boundary condition, porous wall boundary condition. Okay, both of them we had looked at. Today we'll look at interface conditions. And when we say interface conditions, what we mean is how the fluid properties, or rather the flow properties, they match at an interface between two fluids. Okay, so for example, let us say you have a fluid A and a fluid B here, and you have a sharp interface between them. Again, when we say sharp interface, we are modeling this. Uh, excuse me, ma'am. What are you doing? It's okay if you want to continue that work. You can do it in some other classroom. No, what's the point of attendance and then doing something else? No, it's okay. I understand. A lot of assignments and things you guys have to do. So yeah, so I need your focus here because these things will be useful in all of the problems, and maybe hopefully this is the first time you look at surface tension in from first principles, not from atomistic basis, but at least geometrically you'll understand how does surface tension force come about. Okay, and there are some interesting things which I want you to look at here, which are usually taught not in a very correct way in fluid mechanics courses. Okay, so we have a sharp interface. We are assuming that the interface is composed of points. In reality, even when you have water and air, you will have some mass transfer between them. You will have some vapor pressure at the top of water. You will have some water that is evaporating and some water that is condensing. So the interface will not be technically sharp, but from the point of view of a continuum and ignoring all of these mass transfer properties, we are going to assume that the interface is sharp between two fluids. Okay, and so our the question that we want to answer is, let us say this is a fluid A has velocity field UA, and this guy has a velocity field UB. Then what could we say about the interface? Okay, what could we say about how UA and UB, do they have some relation at the interface or no? Okay, so the interface conditions are actually two-part conditions. One is the kinematic interface conditions. One is the kinematic interface conditions, and the other is the dynamic interface condition. As some of you might have guessed, when we say kinematic interface condition, we are interested in looking at how the velocities behave at the interface. When we say dynamic interface condition, we are interested in looking at how the stresses might behave at the interface. Okay. Now, to look at these, let us first consider a control volume. So, this is your control volume. Okay, I made it with dashed boundaries. Let us say this is the surface area in this span-wise, in the lengthwise direction S. Okay, so the surface area is when you multiply this dimension with the depth, and then this is some delta L. Okay, and this control volume is moving with the interface. Okay, so for example, when the interface is like this, let us say the sheet is an interface between the two fluids, then the interface might be moving and deforming. Okay, so what I'm saying is that this control volume is moving with the interface and deforming. So if this is the control volume, it is moving with the interface and deforming. Okay, so this control volume is not fixed, neither the volume is fixed, neither nor it is fixed in space. So it is both translating, rotating, deforming, anything could be happening to this control volume. Okay, so this is V of t. So those of you who might have looked at your practice sheet, second practice sheet, they will know that if we want to derive the governing equations for an arbitrary control volume, so notice that now we are changing our terminologies from a fluid blob or a fluid element to a control volume. Now we are applying it to a control volume. Control volume need not move with the fluid. Okay, control volume is something that you control. You have control on it. You have a choice to make so that you can make your analysis simpler or more difficult, whatever you want. Okay, so control volume is in your hands. It need not move with the fluid. Okay, here we are making it move with the interface, and that is our choice. We are making it move with the interface by choice. It doesn't have to do that. Okay, so if this control volume is, let us say, an arbitrary control volume, then how do we derive, let us say, the governing equation for some intensive property, let us say small phi and then dv. Okay, so how do we derive this? So the idea here is very simple, very similar to what we have considered for a fluid element. So here, instead of taking a fluid element, we will say consider this as a reference configuration of the control volume. Okay, this is reference configuration of control volume, and it is undergoing some deformation. So let me call, we took this as quantity, right? So let's take that only. So q, this is not heat flux vector or anything, this is any quantity per unit volume. Okay, so this is your deformation map for the control volume, and it's obviously going to be a function of time, and I'm not really denoting any material particle, deformed spatial particles here, because there's no point of material particles here. So this is the time varying shape of your control volume. So we apply this, yeah. Control volume is defined by our choice of volume. Volume is fixed by us, fixed not meaning fixed in time or space. We fix it. I could look at, so if this is your fluid in the room, I could look at a control volume that is this big or this big. I could look at a control volume which is starting with this big and then it is deforming some way. So control volume means volume is fixed by us, not fixed in space or time. We choose it, we fix it.
No, I meant volume as a value.
Volume as a value might be changing, but that change is something we decide. It's not decided by the flow.
So initially you have defined S and del L. So they are also changing in time.
Yeah, of course. Everything will be changing in time. So this is what d by dt that we need. So we will again write the same thing. We will try to get it to the reference configuration, some reference configuration, and I will write JV now here. Okay, something like this. And then when you take this inside, when you take the time derivative inside, you will see that you get dq over dt times jv plus q times djv by dt times dv naught. Again, this djv by dt is basically equal to, this is equal to q times del dot. Now here the velocity that I am choosing to define by is using w. Okay, this velocity is not the same as fluid velocity. This velocity would be the velocity of points which make up the control volume, the spatial points which make up the control volume. It doesn't have to be the velocity of the fluid. Okay, it doesn't have to be the velocity of the fluid. It is the velocity of points which make up the control volume, not material points, spatial points. There's no material when we are talking about control volume. We don't need to rely on definition or existence of a material when we look at control volumes. So we get a del dot w, which is the speed of points on the control volume, and now we can apply the same thing here. We get dq over dt plus q times del dot w dv v of t. Now again, what is this dq by dt here? So q as a quantity is now a function of let us call these points as y vectors. Okay, these are spatial points which make up spatial points which compose the control volume. They are not material points, they are not locations of fluid particles at some time t. These are spatial points which are functions of time. So, dq by dt is going to be del q by del t plus dy over dt dot gradient of q. Gradient is with respect to points in the control volume, and this dy by dt is what I have defined as w. So, this is del q by del t plus w dot grad q. And so, when we substitute that here, we get d by dt over an arbitrary control volume q dv to be v of t del q by del t plus del dot q w. Okay. And now we can actually, so we know that del q by del t dv over a control volume. So, if this control volume has some material inside it, if this control volume has some material inside it, then I can write this quantity using the actual Reynolds transport theorem. How? Let us say let q be equal to rho. Okay, sorry. Let q be rho. So, in that case, we know that del rho by del t plus del dot rho u dv, where u is the fluid velocity, is actually equal to 0. But this integration is done over the fluid blob. Now, let us say there is a blob which is inside this control volume. So, I am integrating over Vt, I am integrating del rho by del t over Vt. So, if this is your control volume, it does not matter if your blob actually occupies the whole control volume. Why? Because if the blob is something like this and there is no fluid outside the blob, then of course there is no rho outside the blob, and this integration would eventually become equal to del rho by del t dv b of t, where b of t is the fluid blob that is inside the control volume. It may not be the whole control volume, it may not be occupying the whole control volume, it may be occupying some part of it like this, then this integration would be over this blob, that is it. Okay, you can break a blob in two blobs, that is not a problem. So, this we know is equal to minus of integration over the blob del dot rho u dv, which is going to be equal to minus of del dot rho u dv integration over v of t. And now we can substitute this equal to this in this equation, and we get that d by dt of the mass inside an arbitrarily varying control volume is actually going to be equal to minus of rho del dot of rho u minus rho w dv. There is no restriction about the mass, total mass in a control volume to be fixed. And that is exactly where the whole problem of traditional control volume based derivation of Reynolds transport theorem is, that we say, okay, first in most of your courses, maybe even in your APL 106, it was done like this. You are trying to get this quantity, okay, you are trying to get this quantity. So, this is an integration over control volume, and then when someone substituted q equals rho, they said that, oh, this quantity has to be 0. There is no restriction. Control volume is my choice. If this is my room and I have a control volume that is expanding slowly, is the mass inside that control volume fixed? Is the mass inside that control volume fixed? No, of course not. So there is no reason for mass inside the control volume to be fixed, even in classical mechanics, because control volume is our choice. Okay, it will be fixed only when a control volume's boundaries follow the material particles. It will be fixed only when the control volume boundaries follow the material particles, in which case you will have W equals U and this quantity would be 0, and so this will be 0. If your control volume particles or control volume points are following material particles, then the velocity of those points is equal to velocity of the material particles, which is U. So W equals U and this quantity is 0. But if W is not equal to U, then this is what you get.
So could you explain the BT and V thing? Why it replaced it? The blob.
So the only reason I did that is because this equation I had written for a blob. I had not written it for a control volume. I had not written it for a control volume. So whenever we are talking about this integration inside an arbitrarily control volume, so this is a control volume. This is a material property. So you will be integrating over the whole volume wherever material is, right? That's why I've changed these limits to BT, where BT is the blob or the portion of blob inside the control volume. If there's no blob, if this is empty space, there's some portion of there's blob and rest of it is empty space, then naturally these integration limits will change to this, right? Because otherwise rho is 0. There's no fluid there. That's why I changed it from VT to BT. Basically, it's like you are integrating a function which is non-zero only over a certain range, but you are integrating it from minus infinity to infinity.
It will be valid for any quantity Q, right?
Yeah, of course. It's not necessarily for
We
rho.
can take BT.
Of course, of course. You it doesn't have to be rho. I have taken it rho because this thing simplifies to equal to 0. If I had taken momentum, then I would need forces. But you can write the same way. We are going to use that in the interface boundary conditions. We are going to use that. So we are going to need this. What is d by dt of rho u dv v of t? We are going to need what this is. The main point that I want to bring out is that relative velocity term that you usually see in an arbitrary control volume. This is where it comes from. This is that relative velocity. Okay, what is this del dot of rho u minus rho w dv? Using Gauss divergence theorem, you will write it as rho u minus rho w dot n ds. Okay, so you will write this as minus of rho u minus w dot n ds. This s is not the same. Maybe I'll write this as small s. Okay, so that there's no confusion. This is the whole boundary of the moving control volume, of the deforming control volume. So this is that relative velocity W at the surface, that is the velocity of the control volume points at the surface, and U at the surface, that is velocity of the fluid on the surface of control volume points. So in this example, where let us assume that air in this room is stationary and I have a control volume that is expanding. If air is stationary, U is 0. If air is stationary, U is 0, but is W 0? No, I have a control volume that is expanding. So let us say this is a sphere that is expanding, then you can write that W dot n as the velocity, as the rate of expansion of its radius. Okay, this will be the rate of expansion of the radius. Okay, and so U is 0, W is, let us say, dr by dt, minus minus will become plus. So you get that intuitive answer that what is the rate of increase of mass in a spherical control volume that is increasing. It is equal to rho times dr by dt times ds, which is what you will write very intuitively also. You will take a spherical element, you will say its radius is r, surface area is s, you will do the same things. Okay, so this is how you get the rate of change of quantity in a in an arbitrarily varying control volume, moving or deforming. Okay, so this derivation is actually asked for you as a first problem in the practice sheet. Now the second one, I'm just going to give you the result and I'll expect you to derive it, and that is, so this is rho u minus actually let's write it in a more clean way. So u minus w times u dv. So this is a tensor product. Okay, this is a tensor product here. Plus your, I guess this is not visible, so let me write this here. So d by dt of rho u dv inside this arbitrarily varying control volume will be minus of del dot rho u minus w times u dv plus F, the body force, plus, let's write it as, okay, this is what you will get. So now, yeah, yeah.
The only reason why we are able to replace the integration over Vt with Vt is because we are saying that the mass is only within those blobs inside the control room.
Yeah, exactly. Density, to be more precise. So we will use this to derive our, or to see what we can get for kinematic and dynamic interface conditions. We will use a control volume that is moving with the interface. Okay, a control volume that is moving with the interface. So let us apply our mass equation to this control volume. D by dt rho dv v of t equals minus of del dot rho u, or let me write this in the surface integral form. Sorry. Now let me write this in the limit v of t going to 0. It's not going to 0 in time, it's not like decaying control volume. I am choosing this v of t to be going to 0, to be arbitrarily small. Okay. So in this limit, this quantity is 0, this quantity is 0. What about this quantity? So in the limit v of t going to 0, basically we are looking at in the limit delta L going to 0. That's what this implies. In the limit delta L going to 0, what is this? What does this integration become? Let's say this is your surface 1 and this is your surface 2. So this will become rho u minus w dot n ds over surface 1 plus rho u minus w dot n ds over surface 2. Okay, there is a minus sign in front of both. This has to be equal to 0 because the left hand side went to 0 in the limit of vanishingly small volume. And from here, what do we get? So n of 1 is actually, or n of 2 is minus of n of 1. These will be the same surfaces facing opposite directions. So we get, let's say, rho u minus w dot n 1 ds equals rho u minus w dot n1 ds, this integration over 1, this integration over 2. What do we get from here? What do we get from here? Is this a result? Is this a result? Is this a valid result, or is this some identity? So notice the control volume was moving with the interface. In the limit of this control volume, let us say this is your control volume, in the limit of this control volume shrinking to the limit of being an interface, what is u minus w? 0. This is 0 equals 0. Okay. This quantity is 0, this quantity is 0. The control volume is moving with the interface. It's moving with the interface. So at the interface, as it is shrinking down and becoming an interface, the velocity at the top relative. So the control volume will be moving with the interface. So whatever velocity of the fluid is, that is the velocity of the control volume. So this is what you get. This is basically not giving you anything. Okay, in a lot of in a few lecture notes or in a few videos also you will see this being applied for kinematic interface condition. That's just, that doesn't work. On the other hand, hmm,
What are we actually trying to imply?
and the only thing I am trying to imply is, so this is me flexing myself. Okay, this is me saying that you can't do this. This is wrong. You have to do it properly. And actually, kinematic interface condition cannot be derived. It is a hypothesis. Okay, if you read in old textbooks, you will see that kinematic interface condition cannot be derived. It is a hypothesis. And using this control volume approach, you cannot derive anything. But when we look at dynamic interface condition, we will see that we will actually get a result. Okay, because on the right hand side you will have something in the force equation, you will have these guys, and what we will deduce is that total force on a control volume that is shrink to 0 volume should be 0. That is what we will get. Total force on that control volume should be 0. We will see that in a minute. So now, having shown you that this doesn't work for mass equation, so what works is basically nothing. The kinematic interface condition is a hypothesis, and what we hypothesize is that the fluid velocity, so fluid A and B have equal velocity at the interface. So this is something that we hypothesize. The velocities are equal, not normal only or tangential only, the velocities are equal. Okay. Now, to know what that velocity is, oftentimes what we will need is, let us say these are your coordinate systems, this is 1, 2, 3, and you can define the surface of this interface as x2 equals some c x1 comma x3 comma t. Okay, that is what a surface is, right? Surface equation. So if this is your surface, this is your x2 direction. I am saying x2 varying with x1 or x3 and time. So this is the equation of my interface. Okay. So let me write it in an implicit fashion. The actually this has to be an arbitrary constant. So the equation of the interface is f equals x2 minus c x1 x3 t equals constant. Basically what we are trying to do is, okay, I have hypothesized that the velocities are equal at the interface. What are they equal to? What is this velocity? Can I derive it using the information of how this interface is changing in time? We will need this when we look at instabilities a lot. Okay, so although this discussion is coming like maybe a month or a month and a half earlier than that discussion, but it's still a part of your derivation, so I thought I'll just cover it now. So this is what your f is. This is the equation of surface, or rather interface. So if f is a constant, where f is a function of x1, x2, x3, which are the spatial coordinates, it's a constant. This means df over dt is going to be 0. Where this d is the material derivative, because these x1, x2, x3 are themselves changing in time. So what we get here is del f over del t plus u dot grad f equals 0. Yeah.
x2 minus x2.
So do you understand that this is a surface equation that is changing in time?
So why did you specifically choose x2 since the curvature?
No, I didn't choose x2. So I chose this as the coordinate system, and then I'm defining this as interface. You could, if you can also write that x3 equals c of x1 comma x2 comma t.
That is equally.
Yeah, of course. But that function will change. The function's form will change. The
But you still
analytical.
capture the same surface.
You can, if it's a surface like this. If it's a hemispherical surface or a spherical surface, you can write x1 as square root of r square minus x2 square minus x3 square, or you can write x2 equals plus minus square root of that. I mean, it doesn't matter, right? This is just a choice. Okay. And the result is independent of this choice. The result is independent of this choice. You will see. Huh? F is the implicit form of that surface. So what I did is x2 is this plus c. So I am defining an f which is equal to this, which is constant c. So del f by del t from here, del f by del t will be equal to minus del c over del t plus u dot grad f equals 0 at the interface. So basically, the velocity of the fluid dot with this f is equal to this del c by del t. Now, those of you who remember how to define how to define the normal of an arbitrary surface know that the normal of this surface will be simply gradient of f by mod of gradient f. That is my normal, unit normal. So this means u dot n equals 1 by mod grad f del c by del t. And this is all that we can say about kinematic interface condition. The normal velocities are equal and equal to this at the interface, and since the whole velocity is equal for the two fluids, so the tangential velocities are also equal at the interface. So this is at the interface. Okay, don't apply this. So maybe in some problem I am asking you velocity which is far away from the interface, and some students what they do is they'll just apply this and say, oh, this is velocity. This is all happening at the interface, because f will be constant at the interface. Okay, at an arbitrary location, at some arbitrary surface, f may not be constant. F is the definition of that interface. Okay, so f is constant at that interface, not everywhere. Just like, I mean, if I can define any surface where x1 square plus x2 square plus x3 square will not be constant, right? but if the interface is spherical, then these quantities are constant only on the interface. So, all of this applies at the interface. So, the normal velocity of the fluid A and normal velocity of the fluid B at the interface, they are equal and they are equal to this. Okay. And tangential velocities are also equal, but what are they equal to? That is decided by the problem. We cannot derive anything from here. Okay.
So U here represents what?
Fluid velocity.
On which side?
Huh?
On both sides, one and two.
So, this can be on A or B, on one or two surface, but in, so there is no control volume by the way here, A or B. Okay, this is at the interface. We have said that UA equals UB at the interface, their normal components are equal to this. Okay, this could be either UA or UB, does not matter since both of them are equal at the interface. So, maybe let me write this in equation. Now, let us look at the dynamic interface condition. Okay, let us look at the dynamic interface condition, and for that this control volume equation will be useful for us. Okay, so let us draw a big picture of what this control volume could look like. So, this surface is what I have labeled there as 1, and the bottom surface is what I have labeled there as 2. Okay. Now, there is an interface also. So, this control volume is cutting through that interface. So, here I am making that interface. I am trying to do the best I can with the tools that I have. Maybe this new one will work better. Yeah, okay. So, this is your fluid interface. Okay. And this is that control volume. So, this guy is V of, basically V of t, and we are going to apply our momentum equation on this arbitrary varying control volume in this form. This F is supposed to be a vector. Okay. What we identify is that when you cut through two fluids, we know there is a force called surface tension. Okay, there is a force called surface tension. So, what we will do is we will not write it, we will not combine it here. That force is going to act only at that interface, and the direction in which it acts is that tangential direction. So, let us say here you have that normal. Okay, you have the direction along the curve. So, this is that curve. You have the direction along that curve, let us call it as L hat. Okay. What I am going to add here is another force, which is the surface tension force due to this interface, and that is going to be equal to some coefficient times m hat dl, where this integration is over this curve C. Okay. In our previous discussion, when we did not include this, we did not have a fluid interface. Now that we have a fluid interface, that is an interface between two different fluids, we are hypothesizing that, okay, from basic empirical knowledge, we are saying that there has to be a force which is tangential to this m hat direction, and this sigma is some coefficient. We don't care about that coefficient as of now. And this m hat is defined by L hat cross n hat. Let us first try to simplify this force, and then we will see what happens to the LHS of the. There was a question? No? Let us try to simplify this expression as much as we can, and then we will see how does the how do the quantities simplify for an arbitrary and a shrinking control volume. This is from empirical knowledge. I am saying that if there is a fluid interface between the two, in between the control volume surfaces, then there is a force which is stretching this interface. So it's like there is a interface that I'm trying to stretch. I'm making a control volume pass through this interface. So I'm cutting this. So there's a force due to the stretch. Tension, that is the tension force, right? This is an interface, and there's a tension between the two. This sigma is technically a function of what are the two fluids about which this interface is. If these are two same fluids, then sigma AA is actually 0. That's not really an interface, right? So this, let's try to simplify it a little bit. So we have sigma L cross n dl over this curve C. Okay, so what I'm going to write this as is sigma times n hat, just to, because this sigma is actually a, is there a question?
Sir, that sigma, what I because of surface tension,
Hmm?
the interface, sigma AB, so the physical attribute of that is surface tension.
Yeah, that is the case. We are just going to lead up.
Why not incorporate it with the traction vector?
We will. So that is what I am going to show here. So this we got. So this we got how? We had T dot n ds, right? You will see that this can also be written some force times ds integral over the surface of control volume. So it is indeed a part of traction vector. It is a part of traction vector. Okay, we are going to show that just now. I was actually going to write it, and the thing is, using Stokes theorem, you can show that this guy is equal to. So using Stokes theorem, you can show that this is equal to the surface that this curve is enclosed by. Okay, so the surface that this curve is enclosed by, and that is n cross del cross sigma n. Okay, so this I leave up to you to look at. Which book did you guys follow for vector calculus? Maths 1, Maths 2. Have you guys done vector calculus in Maths 1, Maths 2? Huh? Crazy?
Ross, K. Ross.
For vector calculus? Ross I know is for probability. That is Sheldon Ross. This was a different. Okay, look at that book. The standard book usually is Kreyszig, Advanced Engineering Mathematics, or Advanced Mathematics for Engineers. That is what, there you will find the definition of Stokes theorem. Usually you may be familiar with the Stokes theorem definition, which is like this. So you may be familiar with this, that u dot dl, or let's say u dot l hat dl, where this u is some any, this could be any vector, so let's write it as v. This integration is equal to del cross v dot n ds. Okay. Now the actual Stokes theorem is actually you can remove this dot and replace it with any operation, and this equality sign remains. So you can even replace this with a cross product and this will remain as it is. You can even replace this with a tensor product and this theorem statement will remain as it is. So it is not really holding only for a dot product, it holds for all these operations. Actually same applies to your Gauss divergence theorem, which is in that case doesn't really remain a divergence theorem, it becomes a Gauss's theorem. It doesn't matter what operation you have here, it could be dot, cross, or anything, and using that you can show that these two hold. Okay. So this is what sigma m dl over this curve simplifies to. It is equal to n cross del cross sigma n ds, where this limit, so now I am not integrating it over the closed surface, I am only going to integrate it over this surface if this is my n hat, and over the bottom surface if that is my n hat. Okay. So that is why I have not put a circular sign in that this integral, this is not over a closed surface. Okay. And now this quantity you can actually simplify using the epsilon delta identity. Using the epsilon delta identity you can simplify this quantity. Before we do that, I am going to define a new operator which is the surface gradient operator, that is written like this, which was in your first practice sheet. So this is the definition of my surface gradient operator. Okay, this is how I am defining it. And so what is n hat cross grad s going to give me? If this is the definition of grad s, then what is n hat cross grad s? This, right? Because this is in the direction of n hat. Okay. So I am going to replace this grad with this grad s, and I am going to say that this quantity is equal to n hat cross grad s cross sigma n hat ds. And now when you open this up using epsilon delta identity, you will find that this is actually grad s of sigma minus n hat times the surface divergence of n hat times ds. Okay, this you can show very easily. If you don't want to replace this this nabla with nabla s, it's perfectly fine. You can define this whole quantity in terms of nabla. It will be okay. And now we are very close to a result that you guys are familiar with. But before that, maybe I should define a term which you guys don't know, that minus half of del s dot n hat is actually defined as the mean curvature of a surface.
What is that symbol over nabla s sigma at the bottom?
So this is just the integration, this guy. Okay, this is the definition of mean curvature of a surface. Okay, you can go back to again your vector calculus textbook and see how this is defined. Actually, this is given on Wikipedia also, so you can refer that. This is actually very. So you guys know how to write the curvature of a curve, right? You know that definition of curvature of a curve, right? Dy by dx, d2y by dx square by 1 plus dy by dx whole square, 3 to power 2, those things. This is like the 3D equivalent of that. Okay, this is where it comes from actually. Okay, so this is actually the definition of mean curvature or Gaussian curvature. It is also called Gaussian curvature. Okay, and basically sigma m hat dl becomes plus 2 h n hat sigma ds, and this is basically your surface tension force. Okay, this is something that you guys are familiar with. Okay, you see that that force is in n hat direction. Okay, that force is in n hat direction. So whatever you guys have exposure of surface tension, you know when what you do a jump of pressure. You say that pa minus pb equals 2 sigma by r. Where the hell that 2 by r is coming from? This 2h, that h is 1 by r for that spherical surface. Okay, so 2 by r sigma n hat you will get. N hat is the normal direction, but we also see that there is a tangential force. So this is the tangential component of surface tension, and it is of course 0 if this surface tension coefficient is constant over the interface. If sigma is constant over the interface, grad s is 0, grad s of sigma is 0. So you may have seen these fancy YouTube videos where what they do is they have an interface of between a water and air, and they put an object and they drop something in front of that object and the object starts to move. Okay, so let us say you have this water and air interface, you put some toy boat or something and you drop something on that interface and the boat will start to move. The reason why that is happening is by dropping. So what is in that drop? Usually that drop has surfactants which will change the local surface tension coefficient. So you will have a grad s sigma term. As a result of that, on the interface there will be a tangential force, and that is moving that toy boat. Okay, so you can see these in on YouTube, and that is the tangential component of surface tension. Okay, when you vary the sigma over the interface. So now that we have simplified this sigma m dl to this form, now we are in a state to write my momentum equation over this control volume. This is grad s sigma plus 2h n hat sigma ds. Now we know control volume is moving with the fluid. So this term is 0. In the limit of this Vt going to 0, this term is 0. What we will deduce is that this term will also be 0, because this is finite quantity integrated over an arbitrarily small volume. So this is also 0, and then we will be left with that T dot n ds over the surface of this arbitrarily small control volume. So technically you will get that this over 1 plus this over 2 plus this integral over the interface is equal to 0. Okay, in the limit of Vt going to 0, I applied this momentum equation over the control volume. This term is 0, this term is 0, this term is 0. So we get that, and this is where one of you pointed out that isn't this essentially a traction vector? Yes, it is balancing those traction vectors. T dot n is the traction vector on surface 1, T dot n, this is the traction vector on surface 2. Okay, so we'll pick up from here in our next lecture. And we are very close to the result that you guys know about pressure having a jump due to surface